Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This is a multivariate time series lecture. And this lesson, I'll introduce the estimation of the VAR model. Let's return to the definition of the VAR model. In this formulation, yi is the vector of the ith time series. In other words, if we observe the time series over t time points, it's a t by 1 vector of observations over time. We have n such time series yi, where I indexes from 1 to n. We can write the VAR of order P model in a matrix format for each time series yi, where pi is a matrix of coefficients corresponding to the ith time series, a matrix of the dimensionality of n times p plus 1, since we have n time series and the order of the model is p. We have an additional coefficient for the intercept or the constant. X is the matrix of the lagged time series variables. The matrix X is of dimensionality t by n times p plus 1 matrix, with the tth row given by the lagged m multivariate time series y times t minus 1, t minus 2 up to t minus p. Last, the error term is also a t by 1 vector. We assume that the errors are independent, but the variance depends on I. Let's illustrate the VAR model with the simplest example, a bivariate error 1 model. For this model, we have two model equations, one for each time series. Since the order is p equal to 1, the model is only with respect to y1 t minus 1 and y2 t minus 1. Thus, each regression equation has the same regressors, the same lagged values of y1t and y2t. This is called the unrestricted VAR model because the model corresponds to two regressions with two different variables, but identical explanatory variables. We can estimate this model using the ordinary least square estimation approach separately for each equation. We can write the two regressions in the matrix form as provided in the slide. y1 is equal to x times pi 1 plus the error. y2 is equal to x times pi 2 plus the error term. The matrix X is a t by 5 matrix with each row corresponding to each time point. Given these regression equations, if we apply the ordinary least squares approach used in the standard regression, as you learn in the regression analysis course, the estimated coefficient matrices are as provided on the slide. For example, pi 1 is equal to the inverse of x transpose x inverse times x transpose times y1. Similarly for pi 2 hat. We can extend this estimation approach to a general unrestricted VAR model or order P with n time series. For such a model, we have n regression models, one regression model for each time series. For the first regression model, we regress y1t onto regressors y1t minus 1 up to y1t minus p, y2t minus 1 up to y2t minus p, and so on, ynt minus 1 up to ynt minus p. For the second equation, we regress y2t onto exactly the same regressors, and so on. An important property of the estimation of the VAR P coefficients using the ordinary least square is that the sampling distribution of the estimated coefficients in pi 1 hat, pi 2 hat, up to pi n hat are asymptotically normal distributed, where asymptotic means that this applies under a large sample size. If we do not observe the time series of a large number of time points, then the normality of the estimated coefficients will hold only if the data are normally distributed. This statistical property is particularly important when testing for statistical significance of a subset of coefficients. The classic testing procedure is the so-called Wald test. The two common settings when we would apply this test is in these two examples on the slide. In the first example, we're interested in testing whether all the coefficients corresponding to the kth time series yk are 0 in the nth regression or for the nth time series. The null hypothesis is that all coefficients are 0, where the alternative is that at least one is not 0. I will illustrate this test in a different lesson when we'll discuss the concept of grandeur causality. A second setting is to test the statistical significance of all the coefficients corresponding to the p-order of the time series. The null hypothesis is that all the coefficients corresponding to the p-order are 0 versus the alternative is that at least one is not 0. This test can be used in deciding whether to reduce the VAR model to a lower order VAR model. Generally, for such tests, if the p-value of the test is small, we reject the null hypothesis and thus at least one coefficient is statistically significant. The testing procedures discussed in the previous slide can be used to reduce the unrestricted VAR model to a model with selected coefficients in order to fit a smaller model. This results in what is called the restricted VAR model. Thus, a restricted VAR might include some variables in one equation and other variables in another equation, where an equation corresponds to one regression of one time series. Old-fashioned microeconomic models, so-called simultaneous equations models of the 1950s, 1960s, 1970s, were essentially restricted VAR models. The restrictions and specifications were derived from simplistic macro theory, for example, the Keynesian consumption functions, investment equations, and so on. Sims was the first to be the proponent of the unrestricted VAR model in his book published in 1980s. However, when there is contemporaneous correlation, it may be more efficient to estimate the regression equations jointly rather than to estimate each one separately using the least squares approach. The appropriate joint estimation technique is a so-called generalized least squares, or abbreviated GLS. It has been shown that there are two conditions under which the ordinary least squares applied to each equation separately is identical to GLS, to the generalized least squares approach. One is when there is no contemporaneous correlation among the n time series. The second is when the equations of the regressions, of the end regressions, have the same regressors. In other words, x is the same for all regressions, which is equivalent to the unrestricted VAR model. This motivates using the unrestricted model because it's less computationally expensive. The generalized least squares, it's more computationally expensive. Thus, unrestricted VAR can be simply estimated using OLS even when there is contemporaneous correlation, while the restricted VAR will need to be estimated using GLS. Sims, who was the first to provide more grounding to the unrestricted VAR model, argued that old-fashioned macroeconomic models, particularly using restricted VARs, the restrictions in such models have no substantive justification. Sims argued that economists should instead use unrestricted models. He proposed a set of tools for use and evaluation of VARs in practice. But the VAR model doesn't have only advantages, it also has some limitations. Some of the advantages are that it is easy to estimate, it has good forecasting capabilities. If there is a relationship between time series and there is no need to specify which variables are endogenous and which are exogenous. all are assumed endogenous. I will introduce the concept of endogeneity in a different lesson when I will discuss Granger causality, but in short, it means that the unrestricted VAR assumes that each time series will have a lagged relationship with all of the other n-1 time series. But the unrestricted VAR has also some limitations. It has many parameters. If there are k equations, k time series, one for each time series, and p lags in each equation, there are k plus p times k squared parameters to be estimated. There may be cases when we actually would have less observation than the number of coefficients that we need to estimate, and thus a smaller p will need to be considered. VAR models are also atheoretical since they use little economic theory. Thus, VAR models cannot be used to obtain economic policy interventions. In summary, in this lesson, I contrasted the unrestricted VAR model with the restricted VAR model, and I pointed out properties of the unrestricted VAR model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This is a multivariate time series lecture, and this lesson I will illustrate the estimation of the VAR model using a simulation study. We'll return to the simulation study introduced in a previous lesson. In the simulation, I simulated 3 time series following a VAR model of order 1. We'll like to see how close the estimated coefficients are from the true ones provided by phi. The most common R command used to feed a VAR model is the var R command from the VARs library. The input in the VAR function is a matrix of time series where each column corresponds to 1 time series and each row to 1 time point. We also need to specify the order. Here I use p equal to 1 since we know that the data that was simulated was from a VAR 1 model. The output of this R command is quite complex. I'm showing you here only a portion of the output. Here we see the estimation results for the first time series. The output looks very similar to that from fitting a linear regression model since the VAR function does just that. It applies the ordinary least squares to each individual time series. The output provided here provides the estimated coefficients, the estimates of the pi 1 matrix, as in the model notation in the previous lesson. We also have the standard errors of these estimates and the p-value of the t-test of statistical significance in the last column. What can we learn from this output? From the previous slide, the coefficients from the simulated model, hence the true parameters, are 0.5, 0, and 0 as provided by the first column in the matrix phi. In contrast, the estimated coefficients in the first column of the output are 0.526, 0.007, and minus 0.0028. The estimated coefficients are close to the true ones, but the question is, are they close enough? To address this question, we could perform hypothesis testing. For example, to test whether the coefficients corresponding to the lag 1 of the series, the time series 2, and the time series 3 are not statistically significant. To do so, we can look at the p-values for the 2 coefficients, which are 0.82 and 0.06. Thus, at the significance level 0.05, both coefficients are not statistically significant, thus plausible 0. The output for the other 2 time series is here. The one on the left is for the time series 2, and the one on the right is for time series 3. Similar to the output for time series 1, they provide information on the estimation coefficients and the p-values for the t-test for their statistical significance. For the time series 2, the true parameters are 0, 0.1, and 0, as provided in the second column of the pi matrix in the simulation. The estimated coefficients are 0.02, minus 0.01, and 0.01. The p-values of all 3 coefficients are large, indicating that they are not statistically significant, whether they're plausible equal to 0. In this case, we thus miss to accurately estimate pi to 2. For time series 3, the true parameters are 0, 0, and 0.97 as provided in the third column of the pi matrix. The estimated coefficients are 0.02, 0.008, and 0.96, where both first two coefficients are not statistically significant since their p-values are large, and thus are plausible equal to 0 as in the simulation model. The output also provides information on the covariance matrix of the residuals, which is an estimation of the variance of the error terms, sigma. We can compare this output with the covariance of the simulated model provided below. The estimated covariance accurately captures the contemporaneous dependence among the three time series as provided by the comparison of the values of the two matrices, the true covariance and the estimated covariance. Next, we'll take a closer look at the residuals of the VAR model fit. For that, we can use the residuals R command to extract the residuals which are approximate of the error terms of the three regressions. The residuals of the three regressions all stack up into one vector. We can assess the normality using the hypothesis testing procedure, where the null hypothesis is that the data, the residuals in this case, are normally distributed. For this, we can use the normality.test R command. We can also evaluate whether the residuals have constant variance by applying the arch-test R command, which is a hypothesis testing procedure where the null hypothesis is that the residuals have constant variance. For both, we seek large p-values, that is, we do not want to reject the null hypothesis. This is the R output from these two tests. The normality test provides inference on multiple aspects of normality, including skewedness and kurtosis, where the former is a measure of departure from symmetry and the latter is a measure of a departure from normal tails. The p-values for the normality test are all larger than 0.05, indicating that we do not reject the null hypothesis of normality. Similarly, for the arch test, the p-value is large, indicating that we do not reject the null of constant variance. We can also plot the residuals. Here I'm looping over I from 1 to 3 and plot the residual plot and the normality probability plot for the residuals of each of the three regressions of each of the three time series. Here are the plots. There is not a departure from constant variance or normality, as also provided by the testing procedure from the previous slide. Another assumption to be evaluated is the independence assumption. To note that we cannot evaluate independence, but we can assess whether the residuals are uncorrelated. We can do so through studying the autocorrelation plots, but also using a hypothesis testing procedure for uncorrelated data called serial test in R. The null hypothesis of this test is that the residuals are uncorrelated. This is the output of this test. We discussed this test before for univariate time series. The p-value is large, indicating that the residuals are uncorrelated. Hence, it is possible to have modeled the serial correlation in the three time series appropriately. These are the autocorrelation and cross-correlation plots. The autocorrelation plots indicate that the residuals from each of the three time series look like white noise. Interestingly, the cross-correlation plots show that there may be some contemporaneous correlation among the residuals, since the bar of the zero lag is outside of the confidence band. In summary, in this lesson, I illustrated the estimation of the VAR model using a simulation study. Thank you.